The exponential form of a complex number is e to the I theta. But what does e to the I theta mean? Surely there's no way we can raise any number to a complex power. Multiplying 2 by itself an imaginary number of times seems impossible. You can make a start with the number e by raising it to a real power theta. This will give you the exponential series. And you could plot each term on the number line. 1 theta, theta squared over 2 factorial, and as the terms get smaller, you end up at a point which represents the value of e to the theta. But what about e to the I theta? Where will the point end up if each theta in the series becomes I theta? Well, one is unaffected. The next length is theta, but I theta is in a different direction. And now you're plotting in the complex plane. What about the next term? We've already got the magnitude, theta squared over 2 factorial. I just changes the direction, and I squared is -1. So it's this term that must be added to the series. The next term will also remain the same size, but has to account for I cubed. It's the power of I that fixes the direction of each term. Eventually, you'll end up with a point in the plane representing e to the I theta, just as a real series gives e to the power theta. And the same series will define e to the I theta. So you can make sense of e raised to a complex power, and you can plot it as a point in the complex plane. But this point has quite fascinating properties. If you measure the distance of the point from the origin, it turns out to be exactly 1. And if you measure the angle in radians, it's exactly theta. And this is something that we can show geometrically. Plotting the series for any value of theta, you can measure distances and show that our point is exactly 1 unit from the origin. But what about the angle? How can you check the claim that it's equal to theta? By careful measurement, you'd find that the length theta is exactly equal to the arc. But the radius is 1, so the arc gives a direct measure of the angle. So e to the I theta is a point 1 unit from the origin at an angle theta. And you could find the coordinates of this point using sine theta and cosine theta. But there's another way of arriving at these coordinates, an algebraic way, which you can investigate afterwards. And it uses the series for e to the I theta, and the clue is to examine the real and the imaginary parts separately. The real terms of the series correspond to the horizontal distances. And adding, you'll discover a series which just gives cosine theta. Similarly, the complex terms, the odd powers of I, will also give a series. And this will turn out to be I sine theta. So now you have this complex exponential function, which is e raised to an imaginary power. And it's expressed as a point in the complex plane. And so you can write it in terms of things that you know about. E to the I theta is cos theta plus I sine theta. Now, of course, the question is, what are the properties of e to the I theta? For instance, does this imaginary power behave like a real power?
The exponential function e to the I theta has some extremely interesting properties, and they all arise from the fact that theta is an angle in the complex plane. Graham's just shown us that e to the I theta can be expressed in terms of the cosine and the sine functions. One consequence of this relation is that any complex number can be written in terms of the exponential, e to the I theta. On its own, e to the I theta is a distance 1 from the origin at an angle theta. Multiplying by r just multiplies the real and imaginary parts by r. The new point is r cos theta plus ir sine theta, so the diagonal is r. And r e to the I theta is a complex number, distance r from the origin, at an angle theta. This gives a new way of writing complex numbers, and the two ways are connected by this relation. The Cartesian form, x plus iy, is convenient for addition and subtraction, and the exponential form, r e to the I theta, comes in handy for multiplication and division. We've just said that this exponential form is useful when dealing with multiplication. To see that, let's take any complex number z and multiply it by e to the I theta. Well, we can write z in its Cartesian form. And multiplying out, we get these two terms, x and iy, both multiplied by e to the I theta. Let's plot these two terms separately. Where's x e to the I theta? Well, that's easy. It's just at a distance x and an angle theta. But what about iy e to the I theta? That's a bit more difficult. So let's look at that in more detail. Well, we can expand the exponential as cos plus I sine, and so we get these two terms. We can plot that, imaginary part iy cos theta and real part minus y sine theta. So where's iy e to the I theta? It's just at the corner of the rectangle. OK, let's look at this rectangle. This side has length y sine theta and this one y cos theta. So the diagonal, that's length y. And where's the angle theta this time? Well, it's just the angle to the imaginary axis. OK, let's put that back onto our diagram. iy e to the I theta has got an angle theta with the imaginary axis. OK, to get x e to the I theta and iy e to the I theta, what we've done is we've rotated x and iy both through angles theta. So to get their sum, well, we just rotate z through the same angle theta. And there we are. That's an important property. If you multiply any complex number z by e to the I theta, the effect is that you rotate z through the angle theta. That's multiplication expressed geometrically. What does it look like algebraically? Let's start with e to the I alpha. What do you get if you multiply this e to the I alpha by e to the I theta? You'll have to rotate it through an angle theta. And the number you end up with is the product. But what is this number? It's distance 1 from the origin and at an angle alpha plus theta. And so the product is e to the I alpha plus theta. So to multiply e to the I alpha by e to the I theta, we simply add the powers, which is exactly what you would do for real powers. So how would you solve this problem? Well, 2 times 3, that's 6. And to multiply the exponentials, we just add the powers. And that's all there is to it. So multiplying complex numbers in exponential form, that's easy. The imaginary powers of e behave exactly like real powers.
So now we've got two forms of complex numbers. The Cartesian form is good for addition and subtraction, and the exponential form is good for multiplication and division. And of course, if it's good for multiplication, it should be good for finding powers. To find the product of two complex numbers, we need a magnitude and an angle. For the first part, we simply multiply the magnitudes. What would you expect the angle to be? It's made by summing the angles. But what if r1 equals r2 and θ1 equals θ2? What do you get now? And what would you guess for the nth power? As an algebraic formula, this looks obvious. But what does it look like geometrically? We won't worry about r for the moment. We'll just look at powers of e to the I theta. That's e to the I theta at an angle theta. To multiply by another e to the I theta, you rotate through a further angle theta. For the cube, just multiply by e to the I theta again. And this way, you can build up powers of e to the I theta. The fourth power. The fifth power. But the angle here is just 5 theta. So this point can also be written e to the I 5 theta. Well, this seems all pretty straightforward, both algebraically and geometrically. But what do you get when you put cos theta plus I sine theta in there? So this becomes cos theta plus I sine theta to the power n, from there to there. And the e to the I n theta, well, that becomes cos n theta plus I sine n theta. Now, I think that this result is truly amazing, because on the right-hand side, you've got multiples of the angle, but on the left-hand side, you've got the original angle itself. Well, it's so useful that it's actually given a name, and this formula is called de Moivre's theorem. And to show you how useful de Moivre's theorem is, we're going to give you 2 problems to do after the program. How would you prove that cos 2 theta equals cos squared theta minus sine squared theta? Well, cos 2 theta is the real part of e to the I 2 theta. And what does e to the I 2 theta equal? And it's the real part of e to the I theta squared which gives the answer. Now, if you're not sure how to go to the exponential form and back again, just remember e to the I theta equals cos theta plus I sine theta, and then use de Moivre's theorem. Well, here's a second problem. Prove that sine 3 theta equals 3 sine theta minus 4 sine cubed theta. How do you do that? Well, here's a hint. Well, when you try that, you'll find that a big advantage of complex numbers is that they simplify trigonometric proofs. You see, they don't actually tell us anything new in trigonometry, but they certainly make life a great deal easier. Well, the investigation so far has involved multiplication of complex numbers and finding powers. But if one can find nth powers, for example here, the 5th power, we should be able to work backwards and find the nth roots of a number. So let's start with an easy number, the number 1. What are its square roots? And what are its 4th roots? Well, they're just the square roots of the square roots. Now, what about the cube roots? Well, there's 1, of course. But should there be a pattern here? Are there some more cube roots? Well, how many cube roots of 1 would you expect? We'll see that the problems of finding cube roots of any complex number yet again makes use of the exponential form and de Moivre's theorem.
We'll start with our old friend e to the I theta and see what cube roots we can find. So we've got to find a number which, when cubed, gives e to the I theta. It's easy to find one cube root. We take the angle theta and divide it by 3, and we've got e to the I theta over 3. If we square it, we get e to the I 2 theta over 3, and if we cube it, we get e to the I 3 theta over 3. So e to the I theta over 3 is certainly one cube root, but are there any more? We'll now use a computer to explore this process of finding cube roots. Let's see if it can find any more for us. Given a complex number, e to the I theta, a cube root can be found by dividing theta by 3. The angle on the right is always 1/3 of theta, And however we change theta, the right-hand angle changes by 1/3 of the amount. So, for any e to the I theta, there is always a cube root on the right. The number on the right, what's it the cube root of? It's 1/3 of the angle on the left, theta plus 2 pi. But this complex number is the same as the one we started with. So this number on the right must be a second cube root of e to the I theta. What if we go round another 2 pi? We're back where we started from, but this time we've gone through an angle theta plus 4 pi, and taking 1/3 of this angle gives us a third cube root. However, any further additions of 2 pi simply recreate the same cube roots we have already found. So, given any complex number, e to the I theta, it's got exactly 3 cube roots. One at an angle of theta over 3, and the other two thirds of a revolution further on. Now, on this little machine, I can dial up any number on the left, and the right-hand dial gives me its 3 cube roots. The machine's so designed that whatever change I make to the angle on the left, then 1/3 of the change results on the right. Okay, well, I can use this machine to solve our original problem, which was to find the cube roots of 1. So let me dial at 1 on the left. There we are. And here are the 3 cube roots. Theta equals 0, theta equals 2 pi over 3, and theta equals 4 pi over 3. Now I can write these 3 cube roots in their Cartesian form. E to the 0, that's easy, that's just 1. For the other two, I can use cos plus I sine. So the second one is the cos of 2 pi over 3 plus I sine of 2 pi over 3. And the third one, well, that's the cos of 4 pi over 3 and the sine of 4 pi over 3. So, there are exactly 3 cube roots of 1, as we thought might be the case. Indeed, any number, real or complex, always has exactly 3 cube roots.
Well, so far, we've seen the use of complex numbers, and especially the exponential form, in trigonometric problems involving cos and sine of multiple angles, and in algebra, finding powers and roots. But they can also be used to model physical situations. Now, here's a simple arrangement of switches and light bulbs, and look at this. The current, if I switch this switch on, goes through there, through that bulb, through that one, and back. So when I switch this down, no surprise, both lights go on. If I switch the second switch down, then the current will go right the way through, add to the previous current, and so this light comes on. No surprise. Now, what happens when I switch the third switch down? What do you think is going to happen? Now, that's a surprise. Why should that happen? Well, I think you've probably guessed that this is some special kind of current which is passing through these wires. In fact, it's an alternating current. And before we do anything else, I've got to explain to you briefly what an alternating current is. I can show you what happens with this simple generator. Electric current is generated when a coil rotates in a magnetic field, and the meter shows the current flowing in the coil. But it's not always in the same direction. It flows one way, then the other. And it's said to alternate, and the speed at which it alternates is called the frequency, and depends on the speed of rotation of the coil. Now, a real current alternates rather too fast for us to see it on our model with the light bulbs, so I've replaced the bulbs by meters, and actually I've slowed the frequency down a bit too. Now, watch what happens. There's the first switch. You see the 2 meters at the top going backwards and forwards? That means there's an alternating current through this outside circuit. Now the second one. And we're now adding in a second current, and it's the same frequency, but it's a little bit out of phase. And now the third one, here it comes again. See, the third one is again out of phase, and the needle at the end has stopped moving, which means that there's no current going through that meter anymore. Now, the engineers tell us that this kind of alternating current can be modelled by a cosine function, like this. A cos omega t, t is time, omega is a constant which tells you how fast it goes backwards or forwards, and A is just another constant. Now this one is slightly out of phase, so it's of the same form, but it has a 2 pi over 3, you add on a bit. The third one, again, slightly out of phase, and so you get a 4 pi over 3, moves along a bit. Well, those are the three currents in the wires, and they're all summed here, and the resulting sum is 0 for all values of t. Now, one way to show this is to look at the graphs of these functions. The current follows a cosine curve. As time progresses, the current alternates. The second current is also a cosine, but it's 2 pi over 3 out of phase. It's the same shape, but it's shifted to the left. This curve also gives an alternating current. But this current alternates differently from the first. What will the sum of these two be? Well, it alternates, and it's not 0. Well, that's the top two wires. Remember how these two curves are related. Our third current is a further 2 pi over 3 out of phase. And now we can look at the currents in all three wires at the same time. And amazingly, the sum of these currents is 0.
To complete the solution of Graham's electrical problem, we've got to show that the sum of these three cosine functions is 0 for all values of t. Well, this sum of cosines is just the real part of this expression here. And if I can show that this sum is 0, then the sum of the cosines must certainly be 0. Well, we can factorise this expression. You'll notice that I've taken out the omega t term, which is the alternating part, and we're left with the sum of three complex numbers, which in fact represent the phases of the alternating currents. Well, to add these three complex numbers up, I plotted them. Here they are, and I've already put them into Cartesian form. So adding them up, 1 minus a half minus a half, well, that's 0, and the imaginary parts cancel also. So the expression involving exponentials is certainly 0, and so the sum of the cosines must also be 0. That means that the three alternating currents cancel each other out, and the result? Well, the light goes out.
So there you are. The exponential form of complex numbers is a very effective tool for solving problems involving alternating current. But the exponential form is also useful in trigonometry, and it's given us a relation between multiple angles and powers of cos and sine, and has generally made life simpler in many cases. In algebra, it solves problems involving powers and roots. And in fact, it will even answer the question which we started with at the beginning of this program, and then it seemed impossible: what is 2 to the power I?